Here's a question that might make you uncomfortable. What if you're not as smart as your ancestors? Not your grandparents or great-grandparents. I'm talking about your ancestors from 30,000 years ago. The ones living in caves, hunting mammoths, and painting on stone walls by firelight. What if those people, with no smartphones, no books, no schools, were actually more intelligent than you? More intelligent than all of us? It sounds crazy. I know. We've got the internet. We've split the atom. We've decoded the human genome. We've sent robots to Mars. Surely we're the smartest humans who've ever lived, right? But here's the uncomfortable truth that scientists have been quietly discussing for decades. Human brain size peaked around 30,000 years ago and has been shrinking ever since. Not by a little. We're talking about a loss of roughly 150 cubic centimeters. That's about 10% of our total brain volume. Gone. Vanished over the last 30 millennia. Today, the average human brain weighs about 1,350 grams. But if you could go back in time to the Upper Paleolithic, to the era when humans were painting the caves of Lascaux and Chauvet, you'd find that our ancestors' brains were significantly larger. Some specimens show brain sizes exceeding 1,500 grams. These weren't anomalies, they weren't outliers. This was normal, and it gets weirder. Brain size isn't the only thing that stopped increasing. Our intelligence, our raw cognitive horsepower, seems to have plateaued right around the same time. For hundreds of thousands of years before that, human brains had been getting steadily larger and more complex. Then suddenly, 30,000 years ago, the trend stopped, and not long after, it reversed. If you're using this to fall asleep, perfect. That's exactly why I make these. So maybe subscribe and tell me where you are and what time it is. I love checking the comments and seeing Tokyo at lunch, Toronto at midnight, all these different worlds tuning in at once. Now, you might be thinking this is just some fringe theory, some clickbait pseudoscience. But it's not. The evidence comes from decades of fossil analysis, archaeological discoveries, and genetic studies. Paleoanthropologists have measured thousands of ancient skulls from around the world. The pattern is consistent and undeniable. Human cranial capacity increased dramatically between 2 million and 30,000 years ago. Then it stopped. Then it shrank. This isn't supposed to happen. Evolution doesn't work backwards like this. Intelligence is supposed to be the ultimate survival advantage. Smarter animals should outcompete dumber ones. Bigger brains should spread through the population. Natural selection should favor increased cognitive ability generation after generation. But it didn't. Something changed 30,000 years ago. Something fundamental about how humans lived, what pressures we faced, and what traits actually helped us survive. The really disturbing part, nobody talks about this. It's not in the headlines. It's not trending on social media. But in academic journals and university research labs, scientists have been wrestling with this mystery for years. Some call it the Great Cognitive Decline. Others frame it more carefully as the stabilization of human intelligence. But whatever you call it, the question remains the same. Why did we stop getting smarter? And more importantly, what does it mean for us today? The evidence isn't just in our skulls, it's in our genes too. Studies of ancient DNA show changes in genes related to brain development that occurred right around this critical period. It's in the archaeological record. The sudden shift in how humans lived, what they ate, how they organized their societies. It's even in our behavior today, in the way we struggle with problems that our hunter-gatherer ancestors solved effortlessly. Think about it. Those Ice Age humans had to track animals across vast distances, remembering terrain features and seasonal patterns. They had to identify hundreds of plant species, knowing which were edible, which were medicinal, which would kill you. They had to read weather patterns, predict animal behavior, navigate without maps or compasses. They had to make life or death decisions constantly with no safety net, no second chances. Their brains were tools for survival in the most demanding environment humans have ever faced. And they didn't just survive, they thrived. They created art so sophisticated it still moves us today. They developed complex languages, intricate social structures, and technologies perfectly adapted to their environment. They colonized every habitable continent on Earth. They were us, but in some fundamental ways they might have been more than us. So what happened? How did the human brain, after millions of years of expansion, suddenly hit the brakes and start shrinking? The answer takes us on a journey through the last 100,000 years of human history, from the Ice Age peaks of cognitive evolution through the agricultural revolution and into the modern world. It's a story about trade-offs, survival strategies, and the unexpected consequences of civilization itself. And fair warning, some of what you're about to hear might challenge everything you thought you knew about human progress. Now here's where the story takes an unexpected turn. Because everything we've talked about so far, the bottleneck, the recovery, the expansion, it was all building towards something remarkable. Between about 100,000 and 30,000 years ago, your ancestors achieved something that has never been matched before or since. They became the smartest humans who ever lived. I know how that sounds. We live in the age of smartphones and space stations. We've mapped the human genome and split the atom. Surely we must be smarter than people who lived in caves and hunted. With spears, right? Except the evidence says otherwise, and the evidence is written in the one place that can't lie, the size and structure of our skulls. During the Upper Paleolithic period, human brain volume averaged around 1,500 cubic centimeters. That's substantial. That's impressive. Modern humans, we average about 1,350 cubic centimeters. We've lost roughly 150 cubic centimeters of brain tissue. That's about the size of a tennis ball. That's roughly 10% of our total brain volume, just gone. But it's not just about size. The skulls from this period show something else too. They show different proportions. The frontal lobes, the parts of the brain responsible for complex reasoning, planning, and problem solving, they were more developed. The parietal regions, crucial for spatial reasoning and mental mapping, they were larger. These weren't just bigger brains. These were differently organized brains, optimized for the kind of intelligence that kept humans alive in the most demanding environment imaginable, the Ice Age world. And we can see what those brains were capable of when we look at what these people left behind. Because around 40,000 years ago, something extraordinary happened. Archaeologists call it the Upper Paleolithic Revolution, but that makes it sound too sudden, too simple. What really happened was an explosion of human creativity and innovation, unlike anything the world had seen before or has seen since. Suddenly, the archaeological record is filled with art. Not crude scratches or accidental marks, but sophisticated, intentional, beautiful art. Cave paintings in places like Lascaux and Chauvet in France show animals rendered with such skill and attention to detail that they look like they could walk off the walls. These aren't primitive stick figures. These are works that demonstrate deep observation, technical mastery, and artistic vision. The artist understood perspective, shading, and movement. They mixed pigments to create different colors. They use the natural contours of cave walls to give their subjects three-dimensional depth. Some of these paintings are located deep inside cave systems, hundreds of meters from the entrance, in chambers that would have required sophisticated lighting systems to access. These people were making tallow lamps, carefully managing their fuel, planning expeditions into the darkness just to create art in places that almost nobody would ever see. That's not survival behavior. That's something else entirely. That's culture, meaning, the human need to create beauty and express ideas that transcend immediate necessity. And it wasn't just painting. They were carving, sculptures of animals and humans, some remarkably realistic, others abstract and symbolic. The Venus figurines found across Europe and Russia show standardized artistic traditions that spread across thousands of miles. This means different groups were communicating, sharing ideas, maintaining cultural connections across vast distances. They were making music. Bone flutes from this period show careful manufacture and tuning. These weren't simple noisemakers. These were instruments capable of producing specific notes, probably used in ceremonies and rituals. Some researchers think they can even identify the musical scales these people used, scales that show up in modern music traditions around the world. They were tracking time. Carved bones from this period show regular markings that seem to correspond to lunar cycles. These people were creating calendars, recording the passage of days and months, predicting when resources would be available or when migrations would occur. That requires abstract thinking, the ability to conceptualize time as something that can be measured and recorded. They were developing sophisticated technologies, spear throwers that multiplied the force and range of their weapons, eyed needles for sewing fitted clothing, crucial for surviving in Ice Age Europe, rope and cordage made from plant fibers and animal sinews, sophisticated traps and snares, boats capable of crossing significant bodies of water. Each of these innovations required not just a clever idea, but systematic experimentation, testing, refinement. These people were engineers, constantly improving their tools and techniques. But here's what really tells you about their intelligence: the hunter-gatherer lifestyle itself. Because we tend to think of hunter-gatherers as simple, primitive, struggling to survive day by day. The reality was completely different. Being a successful hunter-gatherer required more raw intelligence, more varied skills, more comprehensive knowledge than almost any occupation in the modern world. Start with navigation. Your ancestors needed to maintain mental maps of territories spanning hundreds, sometimes thousands of square miles. Not simple maps either, but detailed three-dimensional representations that included seasonal variations, water sources, animal migration routes, and plant distributions. They needed to know which hilltops provided the best vantage points for spotting game, which valleys channeled the wind, which ridges would be passable after a heavy snow. They needed to navigate in all weather conditions, often in dense forests or featureless plains, without compass, GPS, or written directions. Studies of modern hunter-gatherer groups show they can navigate with precision that rivals or exceeds GPS systems. Australian Aboriginal people can find water sources in the desert from miles away, reading subtle variations in vegetation and landforms that outsiders can't even perceive. Inuit hunters can navigate across featureless ice, using their knowledge of snow formations and wind patterns. Sand trackers in Africa can follow animal trails that are completely invisible to trained Western observers. These aren't supernatural abilities. These are learned skills, but they require extraordinary perceptual acuity and memory. Then there's ecological knowledge. Hunter-gatherers needed encyclopedic knowledge of hundreds, sometimes thousands of plant and animal species, which plants were edible and when, which were poisonous unless properly processed, which had medicinal properties, which could be used for tool-making, cordage, or construction. They needed to know animal behavior in incredible detail, migration patterns, feeding habits, mating seasons, territorial boundaries. They needed to recognize individual animals and predict their movements. They needed to understand how different species interacted with each other and with the landscape. Anthropologists studying modern hunter-gatherers have found they typically can identify and describe the properties of over 200 plant species and 100 animal species in their territories. But that's just baseline knowledge that everyone in the group shares. Specialists, healers, expert hunters might know hundreds more. And this isn't just memorized information, it's deep, integrated understanding. They understand ecology in ways that most modern biologists don't, seeing connections and patterns that require years of direct observation. The complexity of plant processing alone demonstrates incredible cognitive sophistication. Many wild plants require elaborate preparation to be edible or safe. Acorns need to be leached in multiple changes of water to remove toxic tannins. Certain root vegetables need to be fermented or cooked in specific ways. Some plants are only edible at certain times of year or certain stages of growth. Getting this wrong meant sickness or death. Getting it right required detailed knowledge passed down and refined over countless generations. And then there's hunting. Not just randomly chasing animals, but systematic, strategic hunting that required deep understanding of animal psychology and behavior. Hunters needed to think like their prey, anticipate their movements, understand their responses to different situations. They needed to work in coordinated groups, communicating silently through gestures, each member understanding their role in complex cooperative strategies. They needed to make split-second decisions based on incomplete information. They needed to manage risk constantly, weighing the potential benefits of a hunt against the dangers of injury or getting separated from the group. Modern studies of traditional hunting practices show they involve the same kind of complex problem-solving and strategic thinking that we associate with chess masters or military commanders. Except hunters were doing it in real time, with real stakes, in situations where mistakes meant death. But perhaps the most demanding aspect of hunter-gatherer life was social intelligence. Because humans survived not as individuals but as members of tightly knit groups, and maintaining group cohesion in small communities where everyone knows everyone, where resources are limited and tensions can run high, that required extraordinary interpersonal skills. Hunter-gatherer bands typically range from 20 to 50 individuals, small enough that everyone had direct relationships with everyone else. This created incredibly complex social dynamics. You needed to track everybody's relationships, their histories, their alliances, their conflicts. You needed to predict how different people would respond to different situations. You needed to manage your own reputation, building trust and respect, while navigating status hierarchies and personal rivalries. Conflict resolution was crucial. In a group that small, you couldn't just avoid people you didn't like. You had to find ways to resolve disputes before they escalated. Hunter-gatherer societies developed sophisticated mechanisms for managing conflict. Elaborate gift exchanges, ritual ceremonies, shared storytelling traditions that reinforced group values. All of this required subtle social intelligence, the ability to read emotional cues, understand unstated motivations, and navigate complex interpersonal dynamics. And here's the thing, everyone needed all of these skills. Hunter-gatherer societies couldn't support specialists who only knew one thing. You needed to be a competent tracker, plant gatherer, tool maker, and social operator just to survive. Some people were better at certain skills than others, sure, but everyone needed baseline competence across an enormous range of abilities. These people were the ultimate generalists. Intelligence wasn't concentrated in a few experts while everyone else did simple repetitive tasks. Intelligence was distributed across the entire population, constantly exercised, continuously refined. Physical demands reinforced mental demands. Hunter-gatherers were extraordinarily fit by modern standards. They walked or ran many miles every day across challenging terrain. They climbed, dug, carried heavy loads. Women often carried children while gathering and processing food. Men engaged in intense physical activity during hunts that could last for days. But they weren't just mindlessly exercising. They were constantly making decisions, reading the environment, adjusting their strategies. Physical and mental activity were integrated in ways that modern life almost never replicates. The combination created humans who were physically powerful, mentally acute, and broadly capable across an incredible range of skills. These weren't specialists who knew one thing deeply. These were people who knew hundreds of things competently, who could adapt to new situations rapidly, who could solve novel problems using whatever resources were available. And the brain size reflected this. Because brains are metabolically expensive. Your brain represents about 2% of your body weight, but consumes roughly 20% of your calories. Evolution doesn't maintain large brains unless they provide significant survival advantages. The fact that your ancestors developed and maintained such large brains for hundreds of thousands of years tells you something crucial. Intelligence was absolutely essential for survival. Not nice to have, not a luxury, but fundamental. Natural selection was constantly testing intelligence. Individuals who couldn't navigate got lost and died. Individuals who couldn't identify plants got poisoned. Individuals who couldn't track animals starved. Individuals who couldn't manage social relationships got excluded from the group and died alone. Every generation, the less intelligent were filtered out. Every generation, the genes for greater cognitive capacity were preserved and spread. This created a kind of intelligence that we rarely see in the modern world. Not specialized intelligence focused on narrow domains, but general intelligence capable of handling enormous variety and constant novelty. These people were problem solvers in the purest sense. They encountered new challenges constantly and had to develop solutions using only their knowledge, creativity, and the resources immediately available. By 30,000 years ago, humans had reached what might be called cognitive peak. They had the brain volume, they had the cognitive architecture, they had the cultural systems for preserving and transmitting knowledge, they had the environmental pressures that constantly selected for intelligence. They were the smartest, most capable, most adaptable version of humanity that had ever existed. And then something changed. Something that would alter the trajectory of human evolution forever. Something that would make us smaller-brained, less physically capable, more specialized, and more dependent on technology and social systems. Something that would transform us from ultimate generalists into something else entirely. The agricultural revolution was coming, and it would change everything about what it meant to be human. Around 10,000 BCE, something happened that would fundamentally change what it meant to be human. Not a climate disaster this time, not a genetic bottleneck, not a migration or a speciation event. Something that seemed on the surface like pure progress, pure improvement in the human condition, we invented agriculture. Now, if you've heard this story before, you probably heard it as a triumph. Humans learning to control nature, learning to plant seeds and harvest crops instead of wandering around hoping to find food. The birth of civilization, the foundation of everything that came after. Cities, writing, art, science, technology. And that's all true. Agriculture did make civilization possible, but here's what they don't usually tell you in the celebration of human progress. Agriculture also marked the beginning of the end for human intelligence as we knew it. Because those hunter-gatherers who had survived the bottleneck, who had exploded across 3 continents, who had developed art and language and sophisticated social networks, they were operating at a cognitive level that we modern humans can barely comprehend. Their brains were literally larger than ours. Their intelligence was broader, deeper, more flexible, and agriculture began to systematically erode all of that. Let's start with what agriculture actually meant in practical terms. Before farming, humans lived in small mobile groups of maybe 20 to 50 people. They moved with the seasons, following game, harvesting wild plants, fishing rivers and coastlines. They had to know an enormous amount about their environment. A successful hunter-gatherer needed to identify hundreds of plant species, know which were edible, which were medicinal, which were poisonous, and how those properties changed with the seasons. They needed to understand animal behavior patterns, migration routes, feeding habits, social structures. They needed to track prey across varied terrain, sometimes for days. They needed to predict weather patterns, know where to find water during droughts, understand fire ecology, navigate by stars and landmarks. They needed to make tools from stone, bone, wood, and plant fibers. Not just one kind of tool, but dozens, each adapted to specific tasks. They needed to know how different types of stone fracture, which woods work best for different purposes, how to process plant fibers into cordage strong enough to bind spear points or weave nets. They needed sophisticated social skills, how to maintain cooperation in small groups where everyone was interdependent, how to negotiate with neighboring bands for resources or marriage partners, how to resolve conflicts without violence when violence could get everyone killed, how to teach complex knowledge to children through stories and direct instruction. Every individual needed to be a polymath, botanist, zoologist, tracker, toolmaker, physician, meteorologist, navigator, diplomat, teacher. There was no specialization because there couldn't be. Groups were too small. Everyone needed to know everything because your survival and the survival of your children might depend on any of that knowledge at any moment. This created intense cognitive demands. Your brain had to store and process massive amounts of information. You had to solve novel problems constantly. The environment was always changing, always presenting new challenges. Animals migrated differently. Plants fruited at unexpected times. Droughts forced you into unfamiliar territories. You couldn't just memorize a routine and repeat it. You had to think, adapt, innovate constantly. Now, enter agriculture. At first, it probably seemed like a good idea, maybe a brilliant idea. Instead of following herds and hoping you found ripe berries, you could plant seeds near your camp. Guarantee food would be there when you needed it. You could stay in one place, build more permanent shelters, accumulate possessions that were too heavy to carry. The first farmers, around 10,000 BCE, probably thought they were discovering a better way to live, and in some ways, they were. Agriculture allowed population growth. It created food surpluses that could support non-food producing specialists. It made permanent settlements possible, which eventually led to cities and all the cultural achievements that came with them. But here's what agriculture also did. It began to systematically reduce the cognitive demands on each individual. Consider what a farmer needs to know compared to a hunter-gatherer. A farmer needs detailed knowledge about maybe 5 to 10 crop species, how to prepare soil, when to plant, how to water and fertilize, when to harvest, how to store the results. If you're also keeping livestock, add knowledge about a few domesticated animals, their feeding requirements, breeding patterns, common diseases. That's it. That's the core knowledge base required for agricultural survival. Yes, there are complexities: crop rotation, pest management, weather prediction. But compare that to the hundreds of plant species, dozens of game animals, complex tracking and navigation skills required for successful hunting and gathering. Agriculture represents a massive reduction in the breadth of knowledge required for survival. More importantly, agriculture is repetitive. You plant at the same time every year, you harvest at the same time, you perform the same tasks in the same sequence, season after season, year after year, generation after generation. There are variations, of course, weather changes, pests, diseases, but the basic pattern is predictable in a way that hunting and gathering never was. Your brain no longer needs to solve novel problems constantly. It needs to execute learned routines efficiently. And here's where it gets really interesting. Agriculture created specialization. As settlements grew larger, supported by agricultural surpluses, not everyone needed to farm. Some people could become potters, making vessels to store grain. Others became weavers, creating cloth from domesticated fibers. Some became warriors, protecting the settlement and its stores. A few became priests or chiefs, managing the social and spiritual life of the community. This seems like progress. It is progress in terms of cultural complexity. But notice what happened to individual cognitive demands. A potter doesn't need to know how to farm. A warrior doesn't need to know how to make pots. A priest doesn't need to know how to fight. Each specialist can be incredibly skilled in their narrow domain while remaining ignorant about everything else. In fact, specialization works better when people focus deeply on one skill set, instead of trying to maintain broad competence across multiple domains. For the first time in human history, an individual could survive and reproduce while knowing very little about most aspects of the world. As long as you were good at your specialty and could trade for everything else you needed, you'd be fine. This was revolutionary for society. It's what allowed human culture to develop the complexity that eventually produced writing, mathematics, architecture, all the achievements we associate with civilization. But it was catastrophic for individual intelligence. Because here's the thing about brains. They're expensive. Incredibly expensive. Your brain represents about 2% of your body weight but consumes roughly 20% of your calories. It's the most metabolically demanding organ in your body. Evolution doesn't maintain expensive traits unless they provide survival advantages. When every individual needed to be a cognitive generalist, able to solve diverse problems and store vast amounts of information, large sophisticated brains provided clear advantages. Smarter people survived better, had more children, passed on genes that supported bigger brains and better cognitive function. But once agriculture created specialization, the cognitive demands on most individuals dropped dramatically. You didn't need to be broadly intelligent anymore. You needed to be good at farming, or pottery, or weaving, or fighting. Skills that could be learned through repetition and apprenticeship, rather than requiring constant innovation and problem-solving. Under these conditions, maintaining a large, expensive brain became less advantageous. Individuals with slightly smaller brains consumed fewer calories, but could perform agricultural labor just as effectively as their larger-brained neighbors. Over generations, natural selection gradually favored smaller, more efficient brains. The archaeological evidence for this is striking. If you measure skulls from hunter-gatherer populations before agriculture and compare them to skulls from early farming populations in the same regions, you see a consistent pattern. Brain size begins to decline, not drastically, not all at once, but gradually, steadily, generation by generation. The average brain size of agricultural populations becomes smaller than their hunter-gatherer ancestors. This trend continues right up to the present. Modern humans have brains roughly 10% smaller than humans living 20,000 years ago. That's a loss of about 150 cubic centimeters, equivalent to losing a tennis ball-sized chunk of brain tissue. But the cognitive effect went beyond just brain size. Agriculture changed human nutrition in ways that affected brain development and function. Hunter-gatherer diets were incredibly diverse. Dozens of plant species, multiple types of game, fish and shellfish when available, wild nuts and seeds, occasional honey. This diversity meant they consumed a wide range of nutrients, vitamins, minerals, and fatty acids necessary for optimal brain development and maintenance. Early agricultural diets were radically less diverse. Farmers typically relied on a handful of staple crops: wheat and barley in the Middle East, rice in Asia, corn and beans in the Americas. These crops provided calories, enough to support larger populations than hunting and gathering could sustain, but they provided a much narrower range of nutrients. Most agricultural staples are carbohydrate-rich but relatively poor in the proteins, fats, and micronutrients that brains need. Wheat is low in several essential amino acids. Rice lacks certain B vitamins. Corn is deficient in niacin and tryptophan. Unless these deficiencies are compensated for through other foods, which early farmers often couldn't manage, brain development suffers. We can see this in skeletal remains from early agricultural populations. They show evidence of nutritional deficiencies, stunted growth, weaker bones, more childhood diseases compared to hunter-gatherer remains from the same regions. These are populations that were surviving, even thriving, in terms of population numbers, but they were less healthy as individuals. And childhood nutrition has profound effects on brain development. Deficiencies in key nutrients during critical developmental windows can permanently reduce cognitive capacity. Children who don't get enough protein, essential fatty acids, iron, iodine, and various vitamins during their first few years of life develop smaller brains and reduced cognitive function that persists into adulthood. Agriculture also increased population density, which brought new problems. When humans lived in small mobile bands, diseases had trouble spreading. Infections might kill a few individuals before the group moved on or the pathogen burned itself out. But agricultural settlements created permanent concentrations of humans living in close proximity to each other and to domesticated animals. This was a disease paradise. Crowded conditions, poor sanitation, contaminated water supplies, close contact with livestock that could pass zoonotic diseases to humans. The archaeological record shows that early farmers suffered from far more infectious diseases than hunter-gatherers. And chronic illness is terrible for cognitive development. Children who are sick frequently, who suffer from intestinal parasites or recurring infections, who are fighting constant battles with pathogens, those children don't develop cognitively as well as healthy children, even if they're getting adequate nutrition. Their bodies are diverting resources away from brain development to immune function and fighting infection. Then there's the nature of agricultural labor itself. Farming, especially early farming with simple tools, was brutally repetitive. Ploughing fields, planting seeds, weeding, harvesting, threshing, grinding grain. Hour after hour, day after day, season after season. Compare this to the varied problem-solving of hunter-gatherer life. Tracking an animal requires constant observation, deduction, and adaptation. Which way did it go? How long ago? Is it injured? Where's it heading? You're following clues, making inferences, adjusting your strategy based on new information. It's cognitively demanding work. Weeding a field is not cognitively demanding. It's physically hard, certainly. It requires endurance and strength. But it doesn't require much thinking. You don't need to solve novel problems or make complex decisions. You just need to keep pulling weeds until the field is clear. Agricultural labour exercises the body but not the mind. And brains, like muscles, atrophy without regular challenging use. Agriculture also transformed social structures in ways that reduced cognitive demands for most people. Hunter-gatherer bands were relatively egalitarian. Leadership was fluid and situational. The best tracker might lead the hunt. The person with the most plant knowledge might lead foraging expeditions. The most persuasive speaker might lead negotiations with neighbouring groups. Everyone participated in decision-making because everyone's knowledge and skills mattered. You couldn't afford to ignore anyone's insights when the group was small enough that losing even one person was a significant blow. But agricultural societies quickly developed hierarchies. Chiefs and priests at the top making decisions, warriors and craftspeople in the middle performing specialized roles, farmers at the bottom producing food. This hierarchy meant that most people didn't need to develop leadership skills, strategic thinking, or the complex social navigation required in more egalitarian groups. You just needed to follow orders. Farm when you were told to farm. Fight when you were told to fight. Pay your taxes and your tribute and leave the big decisions to those above you. For the small elite at the top of these hierarchies, cognitive demands might have remained high. Chiefs had to manage complex social dynamics. Priests had to maintain knowledge systems. Early administrators had to develop record-keeping, which eventually led to writing. But these elites were a tiny fraction of the population. The vast majority were farmers performing repetitive labour, following established routines, exercising narrow skill sets in specialized roles. For them, the cognitive demands that had shaped human intelligence for hundreds of thousands of years had simply vanished. And natural selection responds to changing conditions with ruthless efficiency. Traits that aren't providing advantages don't get maintained. The expensive, energy-hungry, cognitively sophisticated brains that had been necessary for hunter-gatherer survival became, in agricultural populations, a luxury that fewer people needed. Generation by generation, the pressure that had been driving human intelligence upward for hundreds of thousands of years reversed. Not suddenly, not catastrophically, but steadily, inexorably. Human brains began to shrink. We were trading intelligence for stability, giving up the cognitive sophistication of our hunter-gatherer ancestors in exchange for the ability to support larger populations, build permanent settlements, and eventually create civilizations. It seemed like a good deal at the time. Maybe it still is. Agriculture made everything that followed possible, cities and science and art and technology. But we paid a price written in our skulls, measurable in cubic centimeters, the price of becoming, on average, slightly less intelligent than our ancestors who painted caves and carved figurines and told stories under ancient stars. So here's where things get really uncomfortable, because up until now we've been talking about theories, archaeological interpretations, behavioral observations. But now we're going to look at the hard evidence, the physical changes in human bodies and brains over the last 20,000 years. And the story they tell is pretty clear. We've been shrinking. Not just getting a little smaller, but undergoing systematic biological changes that suggest our brains, our bodies, and maybe our cognitive capabilities have all been declining since the end of the last ice age. Let's start with the most obvious evidence: skulls. Because here's the thing about skulls, they don't lie. They can't be reinterpreted based on new theoretical frameworks or revised to fit current academic trends. A skull is a skull. You measure it, you record the data, and the numbers are what they are. And those numbers have been making anthropologists uncomfortable for decades. Take a Cro-Magnon skull from 20,000 years ago. These are the people who painted the caves at Lascaux, who survived the last glacial maximum, who carved the Venus figurines and developed sophisticated hunting technologies. Place their skull next to a modern human skull, and the differences are immediately obvious. The Cro-Magnon skull is larger. Not just a little larger, but significantly, measurably, undeniably larger. The cranial capacity, the volume of the brain case, averages around 1,600 cubic centimeters. Some specimens go even higher, 1,700, 1,800 cubic centimeters. Now look at the modern human average. We're sitting at around 1,350 cubic centimeters. That's a decrease of roughly 10% in just 20,000 years. To put that in perspective, 20,000 years is nothing in evolutionary terms. It's like 800 generations. A blip. And in that blip, human cranial capacity has declined by the equivalent of a tennis ball worth of brain tissue. That's roughly 150 cubic centimeters just gone, vanished from our skulls in less time than it takes most species to show any evolutionary change whatsoever. And it's not just one or two outlier specimens making the average look bad. This pattern holds across hundreds of skulls from archaeological sites all over the world. European skulls, African skulls, Asian skulls, all showing the same trend. Bigger 20,000 years ago, systematically smaller as you move forward in time. But maybe brain size doesn't matter, right? Maybe what counts is brain organization, neural density, the efficiency of neural pathways rather than raw volume. That's what we tell ourselves. That's the comforting narrative. But here's the problem with that narrative. When we look at other species, brain size absolutely correlates with cognitive capability. Dolphins have big brains and they're smart. Elephants have massive brains and they show remarkable intelligence. Chimpanzees have smaller brains than humans and show correspondingly less sophisticated cognition. So why would humans be the magical exception? Why would we be the one species where losing 10% of our brain volume somehow doesn't matter? The answer is we probably aren't. That lost volume probably does represent lost cognitive potential. Maybe not in every individual, maybe not in ways we can easily measure with modern IQ tests, but lost potential nonetheless. But let's not stop at just cranial capacity, because the changes go much deeper than simple volume measurements. The shape of skulls has been changing too. Cro-Magnon skulls are more robust. The bone is thicker, denser, heavier. The brow ridges are more pronounced. The jaw is larger and more heavily built. The back of the skull, the occipital region, projects more, providing greater attachment points for powerful neck muscles. Modern human skulls, by contrast, show what anthropologists call gracilization. Our bones are lighter, more delicate, more refined. Our brow ridges are reduced or absent entirely. Our jaws are smaller and more weakly built. The overall bone structure is less robust, less capable of withstanding physical stress. This gracilization isn't limited to skulls either. It's visible across the entire skeleton. Cro-Magnon long bones, the femurs and tibias and humeri, are thicker and show more pronounced muscle attachment sites. Modern human bones are more slender, lighter, less robust. We've basically become the gracile version of our ancestors, the domesticated version if you want to think of it that way. And here's where it gets really interesting. This same pattern of gracilization, robust ancestors becoming more delicate descendants, happens in domestic animals. Take wolves and dogs. Wild wolves have thick bones, massive skulls, powerful jaws. Domestic dogs across almost all breeds have lighter bones, smaller skulls, weaker jaws. The same pattern shows up in wild boars versus domestic pigs, wild cattle versus domestic cows, wild horses versus domestic breeds. The process is called domestication syndrome, and it involves a whole suite of physical changes that appear together when animals undergo selection for tameness rather than survival in wild environments. Smaller brains, lighter bones, reduced aggression, increased sociability. Sound familiar? Because that's exactly the pattern we see in humans over the last 10,000 years. We look like we've domesticated ourselves. But let's get even more specific. Let's talk about teeth. Because teeth tell an incredibly detailed story about diet and lifestyle changes, and the story they tell supports everything we've been discussing. Cro-Magnon teeth are large, really large. Their molars could grind tough plant materials, crack nuts, process raw meat. The tooth roots are long and firmly anchored in massive jaws. The wear patterns on those teeth show they were using them constantly, working hard to process the varied wild foods that made up their diet. Modern human teeth are significantly smaller. Our molars are reduced. Our wisdom teeth, the third molars, don't even erupt properly in many people anymore. We've basically evolved jaws too small to accommodate the full set of teeth our ancestors had. Why? Because we don't need them anymore. Agricultural diets based on processed grains, cooked vegetables, softened meats don't require the massive grinding tools our ancestors needed. The reduction in tooth size correlates almost perfectly with the spread of agriculture. As populations adopted farming, tooth size decreased generation by generation, and this wasn't just environmental change, children eating softer foods and developing smaller teeth. This was genetic change. Selection pressure favoring smaller teeth because large teeth were no longer providing survival advantages. But smaller teeth meant smaller jaws, and smaller jaws meant less space in the skull for the same brain volume. So as our faces became more gracile, our skulls had to compensate. And the compensation came in the form of reduced overall cranial capacity. The brain had to fit into a smaller space. This is where skull shape changes become really important. Cro-Magnon skulls are longer front to back and narrower side to side. Modern human skulls are shorter front to back and wider side to side. We've basically become rounder-headed. Our skulls have had to accommodate the same cognitive structures in a different configuration, fitting them into a more compact space. And different configurations mean different proportions of brain regions. Some areas of the brain get compressed more than others during this shape change. The frontal lobes, the areas associated with planning and abstract reasoning, maintain relatively good volume, but other regions, particularly areas associated with visual processing and spatial reasoning, show more reduction. Is this why modern humans might be less capable at certain cognitive tasks? Tasks that require strong spatial reasoning or complex visual analysis? Maybe. The evidence is suggestive but not conclusive. What we can say for certain is that the physical changes in skull structure have been accompanied by changes in brain organization. Now let's look at the genetic evidence, because over the last decade, advances in ancient DNA analysis have allowed researchers to actually sequence genomes from ancient human remains. And when they compare those ancient genomes to modern ones, the differences are striking. Multiple genetic studies have identified specific gene variants associated with brain size and neural development that have changed in frequency over the last 10,000 years. These aren't random changes, they show clear signatures of natural selection. Specific variants becoming more or less common because they were being selected for or against. One study published in 2010 looked at two genes, microcephalin and ASPM, that regulate brain size during development. Mutations in these genes cause microcephaly, abnormally small brain size. The normal versions help regulate how large brains grow, and the frequencies of different variants of these genes have changed significantly since the agricultural revolution. The variants that were common in hunter-gatherer populations, the ones associated with larger brain size, have decreased in frequency in agricultural populations. Meanwhile, variants associated with slightly reduced brain size have increased. This suggests that after the agricultural transition, there was selection pressure favouring smaller brains. Not massive selection, not the kind of dramatic evolutionary change that creates new species, but steady, consistent pressure generation after generation pushing in one direction. Smaller. Why would evolution favour smaller brains? Because brains are expensive. Metabolically, they're the most costly tissue in the human body. Your brain represents about 2% of your body weight, but consumes roughly 20% of your energy. In an environment where food was abundant and predictable, where survival didn't require constant problem-solving and adaptation, reducing brain size would have been advantageous. You'd need fewer calories to maintain yourself. You'd be more efficient, better adapted to the agricultural lifestyle. Other genetic studies have found similar patterns with genes involved in neural connectivity and synaptic function. Variants that promote more extensive neural networks, more synapses, more complex brain organization, have decreased in frequency since agriculture. Meanwhile, variants associated with more streamlined, efficient neural organization have increased. This doesn't necessarily mean we're less intelligent, but it does mean our brains are organized differently than our ancestors' brains. We might be more efficient at certain types of cognitive tasks, the ones required for agricultural and later industrial society, while being less capable at others, the ones that were crucial for hunter-gatherer survival. The evidence from skull measurements, tooth size reduction, gracilization patterns, and genetic studies all point in the same direction. Humans have undergone significant biological changes over the last 20,000 years, and many of those changes involve reductions. Smaller brains, lighter bones, weaker jaws, reduced muscle mass. We are physically less robust than our Ice Age ancestors. But here's what really drives the point home. When researchers look at the timing of these changes, they don't happen gradually over 20,000 years. They accelerate dramatically after the agricultural revolution. The period from 20,000 to 10,000 years ago shows relatively modest changes. But from 10,000 years ago to the present, the rate of gracilization, brain size reduction, and genetic change accelerates massively. This timing is too precise to be coincidental. Something about the agricultural lifestyle, about settled farming communities and domesticated diets, triggered rapid biological changes in human populations, and those changes have left us smaller, more gracile, and quite possibly less cognitively capable than the hunter-gatherers who painted caves and survived the Ice Age. The skulls don't lie. The genes don't lie. The physical evidence is overwhelming, We have changed, and not all of those changes represent progress. Now here's where things get really interesting and really uncomfortable, because if you've been paying attention to modern society, you might be thinking, wait a minute, we seem pretty smart. We've got smartphones, artificial intelligence, space travel, we're landing robots on Mars and sequencing genomes in our basements. Hasn't human intelligence been increasing, not stagnating? There's actually a famous observation that seems to support this. Throughout the entire 20th century, IQ scores rose by an average of 3 points per decade. Every generation scored higher than the one before. By the end of the century, the average person was testing 30 points higher than their great-grandparents. That's a massive jump. That's the difference between average intelligence and genius level on the old scales. This phenomenon has a name, the Flynn Effect. Named after James Flynn, the researcher who first documented it systematically in the 1980s. And on the surface, it looks like proof that humans are getting smarter, that whatever happened 30,000 years ago doesn't matter because we're on an upward trajectory now. Except that's not what the Flynn Effect shows at all, because here's the thing about those rising IQ scores. They weren't rising evenly across all types of intelligence. When researchers looked closer at exactly which parts of IQ tests were improving, they found something fascinating and deeply revealing. The biggest gains were in abstract reasoning tasks. Questions like, a dog is to puppy as cat is to what? Or, which shape completes this pattern? These kinds of questions showed massive improvement across generations, but tests of basic cognitive processing, reaction time, memory span, spatial reasoning, those showed minimal improvement. Some showed none at all. A few actually showed decline. This tells us something crucial. The Flynn Effect isn't measuring increasing biological intelligence. It's measuring increasing familiarity with abstract thinking and test-taking itself. Modern humans aren't genetically smarter than their great-grandparents. They're just better trained at the specific kind of thinking that IQ tests measure. Think about what changed during the 20th century. Universal education became the norm in developed countries. Children who would have spent their lives doing manual labour were suddenly spending years in classrooms, learning to read, do mathematics, think abstractly. They were exposed to books, newspapers, eventually radio and television and the internet. All of these things train them to think in ways their ancestors never needed to. But this is crystallized intelligence, learned knowledge, acquired skills. It's not the same thing as fluid intelligence, the raw biological processing power that lets you solve novel problems you've never encountered before. To understand the difference, imagine two computers. One is a brand new machine with a fast processor but almost no software installed. The other is an older machine with a slower processor but decades of accumulated programs, databases, and learned routines. Give them both a familiar task that plays to the older machine's stored knowledge, and it'll perform better. But give them both a completely new problem that requires raw processing power. The newer machine wins every time, even though it seems less capable in everyday use. That's the difference between fluid and crystallized intelligence. And the Flynn Effect measures both, but the gains are almost entirely in the crystallized category. So what about fluid intelligence? What about that raw biological processing power? This is where things get uncomfortable. Because when researchers designed tests to specifically measure fluid intelligence, tests that couldn't be improved through practice or education, they found something nobody expected. Fluid intelligence appears to be declining. Not dramatically, not catastrophically, but measurably. Studies from the early 2000s started showing that the Flynn Effect was reversing in developed countries. IQ scores were still rising, but more slowly. In some countries they'd started falling. Even more tellingly, when researchers looked at reaction time data, they found something remarkable. Simple reaction time, how fast you can respond to a basic stimulus, is a pretty good proxy for neural processing speed. It's hard to train. It doesn't improve much with practice. It's about as close as we can get to measuring raw biological cognitive capacity. And we have data on human reaction times going back to the Victorian era. Because 19th century scientists were obsessed with measuring everything, including how fast people could respond to signals, they had mechanical devices that could measure reaction times to within a few milliseconds. When modern researchers compared Victorian-era reaction time data to modern measurements, they found something shocking. The Victorians were faster, not by a huge margin, but consistently, across multiple studies and populations. The average Victorian had a simple reaction time about 10 to 15 milliseconds faster than the average modern person. That might not sound like much, but it's significant. It suggests that raw neural processing, speed, the biological hardware of intelligence, has actually declined slightly over the past 150 years. While we've been getting much better at using our brains, the brains themselves might be running a bit slower. Why would this happen? Several factors might be contributing. First, there's mutation accumulation. Remember, natural selection has essentially stopped operating on human cognitive ability in modern societies. People with lower intelligence have just as many children, often more than people with higher intelligence. In the absence of selection, slightly deleterious mutations accumulate. Most have tiny effects, but over many generations they add up. Second, there's the possibility of technological dependence. Our ancestors relied on their memory because they had no choice. If you didn't remember where the water sources were, you died. If you couldn't navigate by landmarks, you got lost and died. If you couldn't remember complex social relationships, you failed to maintain alliances and your children died. Modern humans don't face these pressures. We have GPS, contact lists, and Google. We've outsourced huge portions of our cognitive load to external devices, and there's growing evidence that this is having effects on our brain structure and function. Taxi drivers who memorize city streets show enlarged hippocampi, the brain regions involved in spatial memory. Stop requiring them to memorize, let them use GPS instead, and those enlarged regions shrink. This isn't necessarily bad. It's efficient. Why waste biological resources maintaining capabilities you can replicate with technology? But it does mean we're probably operating below our biological potential in many cognitive domains, simply because we don't need to operate at full capacity anymore. Third, there are environmental factors. Modern life exposes us to thousands of synthetic chemicals that didn't exist before the 20th century. Many of these are neurotoxic at low doses: lead, mercury, phthalates, flame retardants, pesticides. We've reduced exposure to some of these, increased exposure to others. The net effect on cognitive function is probably negative, though the magnitude is debated. And then there's the educational paradox. Modern education is incredibly effective at teaching specific skills and knowledge. It's gotten much better at this over the past century, but it might actually be making us worse at certain types of fluid intelligence, because education trains you to look for the right answer, the expected response, the pattern the teacher wants you to see. But fluid intelligence, real problem-solving ability, often requires ignoring obvious patterns and looking for unexpected solutions. It requires the kind of divergent thinking that formal education sometimes actively suppresses. Studies have found that children's scores on creativity tests actually decline the longer they're in school,
despite their IQ scores rising. So we have this paradox. IQ
scores rising throughout the 20th century, suggesting increasing intelligence, but reaction times slowing, fluid intelligence potentially declining, creativity decreasing. What's actually happening? The most likely explanation is that we're seeing a massive increase in crystallized intelligence masking a small decline in fluid intelligence. We're getting much better at using the cognitive capacity we have, becoming more practiced at abstract thinking, more skilled at test-taking, more knowledgeable about the world. But the underlying biological hardware, the raw processing power of our brains, is probably no better than it was 30,000 years ago. It might even be slightly worse. This matters because it changes how we think about human cognitive enhancement. For most of the 20th century, there was this assumption that education and enrichment could endlessly improve human intelligence, that if we just had the right curriculum, the right teaching methods, the right educational interventions, we could make everyone smarter. But if most of the Flynn effect is crystallized intelligence, if we're approaching the limits of how much we can improve performance through training, then further gains become much harder. You can teach someone to use their brain more effectively, but you can't change the basic processing speed and capacity they were born with. And if fluid intelligence is actually declining, even slowly, that's a problem we can't educate our way out of. Because fluid intelligence is what you need for genuine innovation, for solving problems that don't have known solutions, for dealing with novel challenges that your training didn't prepare you for. This is why the distinction between enhanced performance and enhanced potential is so crucial. A well-educated modern human with access to computers and the internet can solve problems that would have baffled a genius from 30,000 years ago. But that's because of the tools and the training, not because their brain is fundamentally more capable. Strip away the tools, the training, the accumulated knowledge of civilization, and you'd find that modern humans and ancient humans are probably cognitively equivalent. We might even be slightly less capable at certain raw cognitive tasks because we've lost the constant selection pressure that maintained those abilities. The Flynn effect, then, isn't evidence that human intelligence is increasing. It's evidence that human societies have gotten incredibly good at training and equipping people to use the intelligence they have. The rising IQ scores of the 20th century represent a triumph of culture and education, not evolution. We've built better software, not better hardware. And here's the really sobering part. The Flynn effect appears to be ending. In developed countries, IQ scores have plateaued or started declining. This happened first in Scandinavia in the 1990s, then spread to other European countries, and now appears to be happening in the United States. The causes are debated: changing immigration patterns, declining educational standards, environmental toxins, increased screen time, genetic factors. Probably some combination of all of these, but whatever the causes, it suggests we may have reached the limits of how much we can boost measured intelligence through environmental improvements. We've maximized the crystallized intelligence gains. We've taught people to be as good at taking IQ tests as they're going to get. And now we're seeing the underlying biological reality. The hardware that hasn't meaningfully improved in 30,000 years. This isn't cause for despair. The intelligence we have is clearly sufficient. We built this entire technological civilization with brains that stopped evolving during the Ice Age. But it does mean we should adjust our expectations. We're probably not going to keep getting smarter generation after generation. We've already picked most of the low-hanging fruit in terms of educational and environmental cognitive enhancement. If we want to push human intelligence beyond its current limits, We'll need to do something more dramatic than better schools and cleaner environments. We'll need to either genetically engineer better brains or merge with artificial intelligence, both of which raise profound questions about what it means to be human, but that's a topic for another time. For now, the key point is this. The Flynn Effect doesn't contradict the evidence that human intelligence peaked 30,000 years ago. It confirms it. Because all those rising IQ scores, all that apparent cognitive improvement, turned out to be training and practice, not biological enhancement. We're not getting smarter, we're just getting better at pretending we are. Now here's where things get really strange. Because there's a theory about what happened to human intelligence that sounds absolutely crazy when you first hear it. But the more you examine the evidence, the more sense it makes. What if we didn't just stop getting smarter? What if we actively became tamer? What if, somewhere between 30,000 years ago and now, humans underwent the same transformation that happens to wild animals when we domesticate them? Think about dogs for a second. Wolves are brilliant animals. They have to be. Surviving in the wild requires complex problem-solving spatial memory that would put most humans to shame, and the ability to coordinate sophisticated hunting strategies. Then we domesticate them. And what happens? The average dog can barely remember where you hid a treat 5 seconds ago. They're lovable, loyal, and absolutely terrible at being wolves. Or take foxes. There's this famous experiment in Russia that started in 1959. A scientist named Dmitry Belyaev decided to see what would happen if you bred foxes for just one trait: tameness. Not intelligence, not size, just whether they tolerated being around humans without trying to bite their faces off. He selected the friendliest foxes from each generation and bred them together. Nothing else mattered. If a fox was smart but aggressive, it didn't get to reproduce. If a fox was dumb as a rock but liked humans, it got all the breeding opportunities. Within just 10 generations, something remarkable happened. The foxes weren't just tamer, they were physically different. Their ears started flopping, their tails began to curl, their snouts got shorter, they developed patches of white fur. They started looking less like sleek, dangerous predators and more like, well, dogs. And their brains. They got smaller. Not by a little, by about 15 to 20%. This pattern shows up everywhere we look. Domesticated pigs have smaller brains than wild boars. Domesticated rabbits have smaller brains than wild rabbits. Domesticated sheep, horses, chickens, every single species we've ever domesticated shows the same pattern. Make them tame, and their brains shrink. The question that's been haunting anthropologists for the last few decades is this: did the same thing happen to us? Look at human evolution over the last 30,000 years, and you'll see something striking. We don't just have smaller brains, we have all the other markers of domestication syndrome too. Our faces became flatter, more childlike. Our skulls became more gracile, less robust. Our teeth got smaller, way smaller. Our bones became lighter. We retained juvenile features into adulthood. We developed patches of different hair and eye colours that would never survive in a wild population because they'd make us too visible to predators. We look exactly like a domesticated version of our Cro-Magnon ancestors, like someone took those fierce, brilliant Ice Age survivors and bred them for tameness. But here's the thing. Nobody was breeding us. There was no outside force selecting which humans got to reproduce. If domestication happened, we did it to ourselves. The theory is called human self-domestication, and it works like this. Around 30,000 years ago, human populations were growing rapidly. those small bands of 20 to 30 individuals that had characterized most of human history, were becoming villages of hundreds, then thousands. Living in larger groups created entirely new selection pressures. For millions of years, the most successful humans were probably the most aggressive ones. The individuals who could dominate others, control resources, intimidate rivals. In a small band where everyone knew everyone, raw physical dominance could get you pretty far. But in a large community, extreme aggression becomes liability. You can't just beat up everyone who annoys you when there are hundreds of people around. Try that, and you'll find yourself on the receiving end of a collective punishment. The group will gang up on you, exclude you, or just straight up kill you. So, selection pressure flipped. Instead of favoring the most aggressive individuals, evolution started favoring the most socially tolerant ones. People who could cooperate with strangers, live peacefully in crowded conditions, control their violent impulses. People who were, for lack of a better word, tame. This is where it gets interesting, because tameness isn't just about behavior. It's fundamentally neurological. The same brain structures that control aggression also influence a whole suite of other traits. The key player is something called the neural crest. During early development, neural crest cells migrate throughout the embryo and develop into all sorts of different tissues. They become parts of the face, the teeth, the ears, the pigment cells that determine coloration. They also become parts of the adrenal system that regulates stress hormones and aggression. When you select for tameness, you're essentially selecting for reduced neural crest cell activity, less aggressive stress response. But because these cells do so many different things, you get all these other changes as side effects. The floppy ears in dogs, the curly tails in pigs, the white patches in foxes. They're all neural crest effects, all downstream consequences of breeding for reduced aggression. In humans, the same thing seems to have happened. As we selected ourselves for social tolerance, our neural crest activity changed. Our faces became flatter and more juvenile. Our teeth got smaller. Our bones became more gracile. And our brains, particularly the parts involved in aggression and fear response, started shrinking. The amygdala, that ancient fear center that kept our ancestors alive when saber-toothed cats lurked in every shadow, began to reduce in size. We became less reactive, less hair-trigger aggressive, better at living in close quarters with people who weren't close relatives. But here's the trade-off. The same neural systems that make you aggressive and fearful also drive certain kinds of problem solving. Aggression requires sophisticated forward planning, risk assessment, strategic thinking. A hypervigilant brain is also a brain that's constantly modeling threats, running scenarios, staying cognitively active. Tame that brain down, make it less aggressive and fearful, and you might lose some of that raw computational power. You become calmer, more socially adept, better at cooperation, but maybe a little less brilliant at solving novel problems that don't involve other people. This is exactly what we see in domesticated animals. Dogs are amazing at reading human social cues. They can follow pointing gestures, interpret facial expressions, understand emotional tone in ways that wolves just can't. They've traded raw problem-solving intelligence for social intelligence. The same trade-off might have happened in humans. As our groups got larger and social cooperation became more important than individual brilliance, evolution favored people who were good at getting along, not necessarily good at inventing new technologies. Think about what traits would make you successful in a large agricultural village 10,000 years ago. You needed to cooperate with dozens of unrelated individuals. You had to share resources fairly, follow social norms, control your temper when your neighbour's goat ate your crops. You needed to read social situations, navigate complex hierarchies, remember who owed whom favours. Someone who was brilliant but antisocial would struggle in this environment. Someone who was moderately intelligent but highly cooperative would thrive. Over hundreds of generations, this selection pressure would favour social intelligence over raw cognitive power, and the evidence suggests that's exactly what happened. Archaeological sites from after the agricultural revolution show something fascinating. The variation in human skull shape decreases dramatically. During the Ice Age, you see huge diversity in skull shapes and sizes, suggesting diverse selection pressures in different environments. After agriculture, skulls become more uniform, more gracile, more domesticated looking. It's like the whole species underwent the same transformation, and it happened fast, far too fast to be driven by gradual environmental changes. It had to be driven by something more immediate, more consistent across all human populations. Social selection. Humans choosing other humans as mates and allies based on their ability to cooperate, not their raw intelligence. There's even evidence in our genes. Researchers have identified several genes associated with the domestication syndrome, genes that affect neural crest development and stress response. And many of these genes show evidence of recent positive selection in human populations, meaning they were actively favoured by evolution in the last 30,000 years. One gene, called BASE-YUN-B, is involved in the development of the face and brain. Mutations in this gene are associated with Williams-Buren syndrome, a condition that makes people extremely friendly and socially fearless, but also intellectually disabled. People with this syndrome have the domestication trade-off cranked up to 11, maximum social tolerance, reduced cognitive ability. The fact that genes like this show recent selection in humans suggests we've been moving along that same spectrum, just more gradually, becoming slightly tamer, slightly more socially skilled, and possibly slightly less cognitively sharp in certain domains. But here's what makes this so mind-bending. If the domestication hypothesis is correct, then the decline in human intelligence wasn't some tragedy. It wasn't us losing something precious. It was the price we paid for being able to live together in large groups, for building civilizations, for becoming the dominant species on the planet. Those Ice Age humans with their massive brains were incredible. They could navigate by the stars, track animals across vast distances, make sophisticated tools with minimal materials, but they probably couldn't live peacefully in a city of 10,000 people. They were too aggressive, too independent, too damn smart for their own good. We traded some of that brilliance for the ability to cooperate at massive scale, to build Rome, to organize armies, to create universities and corporations and governments. All of that requires millions of people who can tolerate each other, follow rules, work together toward common goals. You can't build civilization with a species of aggressive geniuses. You just get constant conflict, everyone convinced they know best, nobody willing to compromise or follow someone else's lead. You need a species of moderately intelligent, highly cooperative individuals. You need a domesticated species. And that's what we became. The physical evidence is overwhelming. Modern humans have smaller teeth than our ancestors, a classic marker of domestication. Our bite force is pathetically weak compared to Neanderthals or even early Homo sapiens. We have shorter faces, more delicate bone structure, reduced sexual dimorphism, meaning males and females look more similar than they used to. All domestication markers. We even have retention of juvenile features into adulthood, something biologists call neoteny. Human adults look more like baby apes than adult apes do. Big eyes, small faces, relatively hairless bodies. These are all features of juvenile primates, features we've kept by essentially arresting our development partway through. And neoteny isn't random. It's one of the most consistent effects of domestication. Tame animals retain juvenile features because tameness itself is a juvenile trait. Baby animals are naturally more curious, playful, and friendly than adults. Domestication selects for animals that never fully grow out of that juvenile temperament. We did the same thing to ourselves. We became a species of permanent adolescents, friendly, cooperative, playful, and less cognitively mature than our wild ancestors. But don't mistake this for simple decline, because what we lost in raw processing power, we might have gained in something equally valuable: emotional intelligence, social cognition, the ability to build and maintain complex relationships with dozens or hundreds of individuals. Modern humans are spectacularly good at cooperation. We can coordinate activities across millions of people, create institutions that persist for centuries, transmit culture so effectively that technologies invented on one continent can spread globally within years. No other species can do this, not even close. Neanderthals were brilliant, but there's no evidence they ever built settlements larger than a few dozen individuals. Those massive Ice Age brains never produced writing, mathematics, or cities. They had the raw cognitive power, but apparently not the social tolerance needed to build large-scale civilizations. We did. Because we became tame enough to live together, cooperative enough to share knowledge, socially intelligent, enough to create culture that could accumulate over generations. The domestication hypothesis suggests that this was the real revolution in human evolution. Not bigger brains, but tamer ones. Brains optimized for social living rather than individual survival. And if that's true, then maybe the question isn't why human intelligence stopped increasing. Maybe the question is, why do we assume intelligence is just about brain size and problem-solving ability? What if the most important kind of intelligence is the kind that lets millions of strangers cooperate to build something no individual could create alone? That's the intelligence of civilization, and it required us to become something we'd never been before, not smarter, not fiercer, but tame. Now here's something that might blow your mind. Your brain, that 3-pound lump of fat and protein sitting in your skull, consumes roughly 20% of your body's total energy. 20%, despite being only 2% of your body weight. Think about that for a second. Your heart, which literally never stops beating from the moment you're born until the moment you die, uses less energy than your brain. Your liver, which is constantly filtering toxins and processing nutrients, uses less. Even your muscles, when you're actively exercising, don't consume energy at anywhere near the same rate per unit of mass as your brain. The human brain is, metabolically speaking, the most expensive organ in nature. No other species has anything like it. A chimpanzee's brain uses maybe 8-9% of its body's energy. A dog's brain, about 3-4%. We're walking around with biological supercomputers that demand constant fuel, massive amounts of it, just to keep functioning. And here's the thing, that fuel has to be the right kind of fuel. Your brain isn't just hungry, it's picky. It needs specific nutrients in specific amounts. Omega-3 fatty acids for building cell membranes, B vitamins for neurotransmitter production, iron for oxygen transport, iodine for thyroid function, which regulates brain development, zinc, selenium, magnesium, dozens of micronutrients that have to be present in the right proportions or the whole system starts breaking down. and for hundreds of thousands of years we were getting these nutrients. Our hunter-gatherer ancestors, the ones who developed those massive brains after the bottleneck, they were eating a diet that modern nutritionists can only dream about. Varied, nutrient-dense, rich in exactly the compounds that growing brains needed. They weren't following some paleo diet plan they found on the internet. They were eating whatever they could find, and what they found was everything. Meat from dozens of different animals, each with different fatty acid profiles. Fish and shellfish loaded with omega-3s and iodine. Wild plants, nuts, berries, roots. Each season brought different foods. Each region offered different resources. A hunter-gatherer living in coastal Africa might eat 200 different species of plants and animals over the course of a year. Different foods every week, sometimes every day. Their bodies, their brains, were getting a constant influx of diverse nutrients in varying combinations. This matters because the brain doesn't just need total calories. It needs variety. Different nutrients interact, enhancing or inhibiting each other's absorption. Iron absorption is boosted by vitamin C. Calcium can interfere with iron uptake. Omega-3 fatty acids work best when balanced with omega-6s. The hunter-gatherer diet wasn't perfectly optimized by design, but through sheer diversity it covered all the bases, and the results were spectacular. Archaeological evidence shows that late Paleolithic humans, the ones living between 100,000 and 10,000 years ago, had larger, more robust skulls than their agricultural descendants. Their teeth were healthier, showing fewer cavities and less wear. Their bones were denser, indicating better overall nutrition. Most tellingly, their brain cases, the part of the skull that houses the brain, were consistently larger than those of the farmers who came after them. Then came the agricultural revolution, and everything changed. Not all at once, not everywhere, but starting around 10,000 years ago in multiple locations worldwide, humans began cultivating grains, wheat in the Middle East, rice in Asia, corn in the Americas. It seemed like a brilliant innovation. Instead of wandering around looking for food, you could stay in one place and grow it. Instead of being dependent on the uncertain movements of game animals, you could plant fields and harvest predictable crops. But there was a catch. Actually, there were several catches, but the one that matters for our story is this. Agricultural diets were monotonous. Instead of eating 200 different species, you were eating maybe 10 to 20, and the vast majority of your calories came from one source. Whatever grain you were cultivating. If you were a wheat farmer in ancient Mesopotamia, you were eating wheat bread. For breakfast, lunch, and dinner. Day after day, month after month, year after year. Maybe you had some vegetables. Maybe you kept some chickens or goats. But the core of your diet, 60, 70, sometimes 80% of your total calories, came from a single grain. This created a nutritional disaster that we're still dealing with 10,000 years later. Grains, any grains, are nutritionally incomplete. They're great for providing raw calories. That's why civilizations built themselves on grain agriculture. You can feed a lot of people with wheat fields, but grains are relatively poor in essential nutrients compared to the wild foods they replaced. Take omega-3 fatty acids, absolutely critical for brain development and function. Wild game meat contains significant amounts of omega-3s because wild animals eat diverse diets, including omega-3 rich plants. Domesticated grain-fed animals, meat is much lower in omega-3s and much higher in omega-6 fatty acids. The ratio shifts dramatically. Hunter-gatherers were probably getting omega-6 to omega-3 ratios around 1:1 or 2:1. Early agricultural populations, more like 10 to 1 or higher. Modern Western diets, we're talking 20 to 1, sometimes 30 to 1. This isn't just a trivial difference. Omega-3 fatty acids are literally the building blocks of brain cell membranes. They affect how neurons communicate, how they form connections, how they maintain their structure. When you don't get enough omega-3s during critical periods of brain development, childhood, adolescence, late-stage pregnancy, the brain doesn't develop properly. It can't. It's like trying to build a house without enough bricks. Iron is another critical nutrient that plummeted in agricultural diets. The most bioavailable form of iron comes from meat, particularly red meat. Plant-based iron from grains and vegetables is much harder for the body to absorb. Iron deficiency causes anemia, which reduces oxygen delivery to the brain. In children, even mild iron deficiency can cause permanent cognitive impairment. Lower IQ, reduced attention span, slower information processing. The effects are subtle but real, and they're irreversible if they occur during critical developmental windows. Archaeological evidence shows that iron deficiency anemia became endemic in early agricultural populations. Skeletal remains show characteristic bone changes indicating chronic anemia. Dental enamel defects suggest periods of severe malnutrition during childhood. These weren't isolated cases. This was happening across entire populations, generation after generation. Iodine deficiency followed a similar pattern. Iodine is critical for thyroid hormone production, and thyroid hormones regulate brain development. Severe iodine deficiency causes cretinism, profound mental disability combined with stunted growth. Even mild deficiency can reduce IQ by 10 to 15 points. Hunter-gatherers living near coasts got plenty of iodine from seafood. Those living inland got it from wild game that grazed on iodine-rich plants. But agricultural populations, especially those living far from the sea and subsisting primarily on grains, often suffered chronic iodine deficiency. Entire regions had endemic cretinism. Parts of the Alps, the Himalayas, inland China, Central Africa. Areas where people were far from the ocean and eating mostly locally grown grains. The cognitive effects on these populations were devastating and largely invisible. How do you know your entire society is cognitively impaired if everyone you know is similarly affected? There's no comparison point. But it wasn't just micronutrient deficiencies. The agricultural revolution brought something else, something that hunter-gatherers had rarely experienced: regular famine. This seems paradoxical. Farming was supposed to provide food security, but it did the opposite. Hunter-gatherers spread their risk. If one food source failed, they had dozens of alternatives. If hunting was poor, there were fish, shellfish, insects, plants. If one region was experiencing drought, they could move to another. Agricultural populations had put all their eggs in one basket, sometimes literally. If the wheat harvest failed, there was no backup, and harvests failed regularly. Drought, floods, pests, diseases, wars. Early agricultural societies experienced periodic famines that killed substantial portions of their populations. And famine doesn't just affect the people who live through it. It affects their children, and even their grandchildren, through a process called epigenetic inheritance. Here's how it works. When a pregnant woman experiences famine, her body makes metabolic adjustments to survive. These adjustments affect the developing fetus, changing how its genes are expressed. The effects are particularly severe if famine occurs during the second trimester, when the baby's brain is developing most rapidly. The fetal brain, sensing that it's developing in a world of scarcity, adjusts its growth patterns, it becomes more efficient, which sounds good, but what it really means is smaller, fewer neurons, fewer connections, reduced capacity for complex processing. These changes are adaptive if the child is actually going to grow up in a world of chronic food scarcity. Better to have a smaller, more efficient brain that can function on limited resources, but they're maladaptive if food availability improves. And here's the really disturbing part. These epigenetic changes can persist for multiple generations. The children of famine survivors, even if they themselves never experience food scarcity, show altered metabolism and potentially reduced cognitive capacity. Their children, the grandchildren of the original famine survivors, can still show effects. We can see this in modern populations. The Dutch hunger winter of 1944 to 1945, when Nazi occupation caused severe famine in the Netherlands, created a natural experiment. Researchers have been following the descendants of famine survivors for 75 years. The children of women who were pregnant during the famine show increased rates of obesity, cardiovascular disease, and psychiatric conditions. The grandchildren show altered metabolism and stress responses. Multiple generations affected by a single year of starvation. This same pattern played out thousands of times during the agricultural period. Famine after famine, each one leaving epigenetic scars on populations that persisted for generations. Hunter-gatherers had experienced periods of food scarcity, of course. The climate bottleneck was proof of that. But it was rare, unpredictable, and they had cultural adaptations to spread risk. Agricultural populations experienced regular, predictable famines as part of the normal cycle of sedentary life. The cumulative effect on human cognition was probably substantial. Then you add in food quality changes beyond just nutrient density. Agricultural populations began eating higher proportions of carbohydrates and lower proportions of protein and fat. This affected brain development in multiple ways. The brain is about 60% fat by dry weight. It needs substantial amounts of dietary fat to develop properly. High carbohydrate, low fat diets provide plenty of calories but insufficient building blocks for growing brains. Archaeological evidence shows that the transition to agriculture was accompanied by a reduction in average height, suggesting chronic protein deficiency. If populations weren't getting enough protein to support optimal skeletal growth, they definitely weren't getting enough to support optimal brain growth, and we haven't even gotten to modern times yet where things get even stranger. The last 150 years have brought unprecedented changes to human nutrition, changes that are happening far too fast for genetic adaptation. The Industrial Revolution brought processed foods, refined grains stripped of most of their nutrients, vegetable oils with skewed fatty acid ratios, sugar in quantities that would have been unimaginable to our ancestors. A hunter-gatherer might consume the equivalent of a few teaspoons of sugar per year, mostly from honey and ripe fruits. Modern Americans consume an average of 17 teaspoons per day. This isn't just causing obesity and diabetes, it's affecting brain function. High sugar consumption is associated with inflammation, oxidative stress, reduced neuroplasticity. Studies show that children who consume large amounts of sugar and processed foods score lower on cognitive tests than those eating more whole foods. The effects are dose-dependent and begin showing up within weeks of dietary changes. But perhaps more concerning are the environmental toxins that have entered our food supply: lead, mercury, pesticides, industrial chemicals. Many of these compounds are neurotoxic, meaning they specifically damage brain tissue. Lead exposure, even at low levels, permanently reduces IQ. There's no safe threshold, no level of exposure that doesn't cause harm. And until the 1970s, Lead was everywhere. Leaded gasoline, lead paint, lead pipes carrying drinking water. Entire generations of children grew up with chronic low-level lead exposure. The average blood lead level in American children in the 1970s was about 15 micrograms per deciliter. Today, any level above 3.5 is considered elevated and triggers intervention. We were collectively mildly lead poisoned for decades. Some researchers estimate that the reduction in lead exposure since the 1970s might account for a measurable increase in average IQ, part of the Flynn effect we talked about earlier. Mercury is another problem. It accumulates in fish, especially large predatory fish like tuna and swordfish. Pregnant women who consume mercury-contaminated fish give birth to children with reduced cognitive abilities. The effects are subtle, but measurable. A few IQ points lost here, slightly slower processing speed there. Multiply that across millions of people, and you have a population-level effect. Then there are the pesticides. Organophosphates, used widely in agriculture, are known neurotoxins. They were originally developed as nerve agents during World War II and later repurposed for killing insects. They work by disrupting nervous system function, and they affect human brains the same way they affect insect brains, just at higher doses. Children exposed to organophosphate pesticides, even at levels considered legally safe, show reduced cognitive abilities and increased rates of attention deficit disorders. Farm worker children who have the highest exposure show the most severe effects, and we're discovering new neurotoxic compounds all the time. Flame retardants in furniture and electronics, plasticizers in food packaging, PFAS chemicals in non-stick cookware and water supplies. Many of these compounds are what scientists call endocrine disruptors. They interfere with hormone function, including thyroid hormones that regulate brain development. We're conducting an uncontrolled experiment on ourselves, exposing every human on Earth to hundreds of synthetic chemicals that didn't exist 100 years ago, and only beginning to understand what they're doing to our brains. The evidence so far isn't encouraging. Studies consistently show that higher exposure to these environmental toxins correlates with lower cognitive function. So let's add it all up. For hundreds of thousands of years, our ancestors ate varied, nutrient-dense diets that perfectly supported the development of those energy-hungry brains that made us human. Then we switched to monotonous grain-based diets that were nutritionally incomplete. We exposed ourselves to regular famines that triggered epigenetic changes lasting multiple generations. We reduced our intake of critical nutrients like omega-3 fatty acids, iron, and iodine, while increasing our consumption of refined carbohydrates and sugars. And in the modern era, we've added environmental toxins that actively damage developing brains. Each factor individually would be concerning. Together, they create a perfect storm of cognitive compromise. Not enough to reduce us to functional disability. We're still smart enough to build civilizations, create technology, write symphonies. But smart enough compared to what? Compared to what we could be if every child received optimal nutrition. If no pregnant woman experienced famine or nutritional stress. If we weren't all carrying body burdens of neurotoxic chemicals. How much cognitive capacity have we lost to poor nutrition and environmental toxins over the last 10,000 years? We can't know for certain, but we can make educated guesses. The difference between adequate and optimal nutrition during childhood is worth maybe 5 to 10 IQ points. Elimination of environmental toxins might be worth another 5 points. Better maternal nutrition during pregnancy could add several more. We're probably talking about a total effect of 10 to 20 IQ points on average, maybe more. That might not sound like much on an individual level, but at a population level it's enormous. It's the difference between a society where 2% of people are cognitively gifted and a society where 10% are. It's the difference between having 100 potential Einsteins in a generation and having 500. And that's just the measurable IQ effects. We're not counting things like creativity, attention span, emotional regulation, mental health, all of which are also affected by nutrition and environmental factors, all of which contribute to overall cognitive function. We are quite possibly functioning at a fraction of our species' potential cognitive capacity, not because of genetic changes, though those matter too, but because we're not feeding our brains what they need to reach their full potential, because we're exposing ourselves to toxins that actively damage brain tissue, because we've created a nutritional and environmental landscape that's hostile to optimal cognitive development. And the tragedy is that we know how to fix most of this. We know what nutrients developing brains need. We know which environmental toxins are most harmful. We have the resources and knowledge to provide optimal nutrition to every child and eliminate most neurotoxic exposures. But we don't, because it would be expensive, inconvenient, and would require systemic changes to agriculture, industry, and food distribution. So we continue limping along with brains that are good enough but not as good as they could be. Hunter-gatherer intelligence, stuck in agricultural bodies, trying to navigate a modern world, all while slowly poisoning ourselves with chemicals our ancestors never encountered. This is the hidden cost of civilization. Not just the loss of genetic potential we discussed earlier, but the ongoing nutritional and environmental factors that prevent us from fully expressing even the genetic potential we still retain. We're living testaments to what the human brain can accomplish, even when running on suboptimal fuel in a toxic environment. Imagine what we could do if we fix those problems. Imagine what we will do if we don't. So here we are, sitting in our climate-controlled homes, staring at glowing rectangles, using brains that stopped evolving 30,000 years ago. And the thing is, those brains weren't designed for this. They weren't designed for spreadsheets and social media, for rush-hour traffic and quarterly earnings reports. They were designed for something completely different. They were designed to track animals across open savanna, to remember which plants were poisonous, to navigate complex social hierarchies in groups of 150 people, to spot patterns in weather and animal behavior that meant the difference between eating and starving. Your brain is a Paleolithic survival machine trying to operate in an information age world. And that mismatch explains so much about why modern life feels the way it does, why we're stressed, anxious, overwhelmed, why we make irrational decisions about money, relationships, and risk, why we can build spacecraft but can't stop doom scrolling at 2 a.m. Because here's the thing about those cognitive adaptations that peaked 30,000 years ago. They were perfect for the environment they evolved in. Absolutely perfect. Natural selection spent hundreds of thousands of years fine-tuning human intelligence for a very specific set of challenges. And then, in the evolutionary blink of an eye, we changed everything about how we live. We built cities, invented agriculture, created writing, developed technology. We transformed our entire environment in less than 10,000 years. Our brains didn't have time to catch up. They're still running on software designed for a world that doesn't exist anymore. Take cognitive biases. We think of them as flaws, as bugs in the human operating system. But they're not bugs. They're features. Features designed for survival in a world where split-second decisions could mean life or death. The negativity bias, for instance. That tendency to focus more on bad news than good, to remember threats more vividly than rewards. Modern life, that's exhausting. It's why the news media can manipulate us so easily, why one criticism stings more than 10 compliments. But 30,000 years ago, that bias was essential. The person who remembered where the lion attacked was more likely to survive than the person who dwelled on where the good berries grew. You could always find more berries. You only had to forget about the lion once. The confirmation bias works the same way. We naturally seek information that confirms what we already believe and ignore evidence that contradicts our worldview. In the modern world, this creates echo chambers, polarization, the inability to update our beliefs in the face of new evidence. But in a tribal society of 150 people, confirmation bias was social glue. It helped you maintain group cohesion, trust your allies, see the world the same way your tribe saw it. Constantly questioning your group's shared beliefs would have made you an outcast, and outcasts didn't survive long. The availability heuristic is another one. We judge how likely something is based on how easily we can recall examples. This makes us terrified of plane crashes but blasé about car accidents, even though cars are far more dangerous. It makes us overestimate the risk of terrorism and underestimate the risk of heart disease. But when you're living in a small territory with limited information, the availability heuristic makes perfect sense. If you can easily remember 3 people being killed by crocodiles at a particular water hole, you should probably avoid that water hole. The things you can remember vividly are probably the things that happen frequently in your immediate environment. Our brains are full of these evolutionary hangers. Social comparison is built into our neural architecture because in small tribes, your relative status determined access to resources and mating opportunities. Now we compare ourselves to carefully curated Instagram profiles and feel inadequate. Loss aversion made sense when losing your stored food could mean starvation, but now it makes us hold on to bad investments and stay in unfulfilling careers. The craving for sugar and fat was adaptive when calories were scarce, but now it's driving an obesity epidemic. We're running Stone Age software on Information Age hardware, and the mismatch is causing errors everywhere. But here's where it gets interesting. Understanding this mismatch gives us power, because unlike our ancestors, we can consciously design our environments to work with our evolved psychology instead of against it. Consider physical exercise. Modern life has made it optional. You can survive perfectly well without ever walking more than a few hundred steps a day. Your ancestors, though, they walked an average of 10 to 15 miles daily, just as part of normal life. Hunting, gathering, moving camp, visiting neighboring groups. That constant low-level physical activity wasn't exercise to them. It was just existence. And here's the critical part. Their brains evolved to function optimally under those conditions. Movement wasn't separate from thinking. It was integrated with thinking. Modern neuroscience is confirming what our ancestors knew intuitively. Physical activity doesn't just make your body healthier, it makes your brain work better. Aerobic exercise increases production of brain-derived neurotrophic factor, a protein that promotes growth of new neurons and connections between them. It improves memory, enhances executive function, reduces anxiety and depression. People who exercise regularly perform better on cognitive tests than sedentary people, even controlling for other factors. Not because exercise makes you smarter than your genetic potential, but because it allows your brain to function at the level it was designed to operate at. Sitting in a chair for 10 hours a day isn't neutral, it's cognitive impairment. The same principle applies to diet. Your Paleolithic ancestors ate an incredibly diverse diet, maybe 300 to 400 different plant and animal species throughout the year, wild game, fish, nuts, seeds, fruits, vegetables, roots, insects. The nutritional complexity was staggering, providing not just macronutrients, but micronutrients, antioxidants, omega-3 fatty acids, and compounds we're only beginning to understand. Modern industrial diets, by contrast, are based on maybe 10 to 15 core ingredients: wheat, corn, rice, soy, a handful of vegetable oils. Even when we eat varied meals, they're built from the same nutritional building blocks, and our brains are suffering for it. Omega-3 fatty acids are particularly critical. These compounds are essential components of brain cell membranes, affecting everything from neurotransmitter function to inflammation levels. Hunter-gatherer diets were rich in omega-3s from fish, wild game, and certain plants. Modern diets, especially in Western countries, are dramatically deficient. Studies consistently show correlations between omega-3 intake and cognitive performance, mental health, and protection against cognitive decline. Simply getting adequate omega-3s won't make you smarter than your genetic potential, but being deficient will absolutely make you dumber than you should be. Novel experiences and challenges work similarly. Your ancestors lived in a constantly changing environment. Every day brought new problems to solve. Track an animal you'd never hunted before. Figure out whether a new plant was edible. Negotiate with a group you'd never met. Navigate to a place you'd only heard described. Their brains were constantly learning, adapting, making new neural connections. That's the environment human cognition evolved in. An environment of perpetual novelty and challenge. Modern life for many people is the opposite. The same commute, the same job tasks, the same social interactions, the same entertainment. We've optimized for efficiency and predictability, but our brains don't thrive on predictability. They thrive on challenge. Neuroplasticity, the brain's ability to form new connections and reorganize itself, doesn't disappear in adulthood. But it does require stimulus, novel experiences, challenging tasks, learning new skills. These aren't luxuries, they're maintenance. They're what keeps your Paleolithic brain functioning in the modern world. This is why learning a new language, taking up a musical instrument, or developing a complex hobby like chess or programming correlates with better cognitive function across the lifespan. Not because these activities make you inherently smarter, but because they provide the kind of cognitive challenge your brain was designed to have. They create the neuroplasticity that would have happened naturally in an ancestral environment, but requires conscious effort today. Social connection works the same way. Humans evolved for face-to-face interaction in stable social groups. We're exquisitely sensitive to facial expressions, vocal tone, body language. Entire regions of our brain are dedicated to social cognition, theory of mind, understanding what others are thinking and feeling. But modern social environments are mismatched with these evolved capacities. We try to maintain meaningful relationships with hundreds of people through digital interfaces that strip away most of the social information our brains evolved to process. We form parasocial relationships with celebrities and influencers, activating social cognitive circuits with people who don't even know we exist. We experience social rejection through text messages and social media, triggering emotional responses designed for face-to-face exclusion from critical social groups. The research is clear. Quality of social relationships is one of the strongest predictors of both cognitive function and longevity. People with strong social connections perform better on cognitive tests, experience less cognitive decline with age, and have lower rates of dementia. Again, this isn't because socializing makes you smarter. It's because your brain is a social organ, designed to function within a network of other brains. Isolation isn't neutral, it's cognitive degradation. But here's where modern life offers something unprecedented. Technology. Yes, the same technology that creates mismatch problems also offers solutions. We can use technology as cognitive enhancement, compensating for the limitations of our evolved brains. Writing was the first major cognitive enhancement technology. It gave humans external memory storage, allowing knowledge to accumulate across generations without relying on individual memory capacity. Now we have smartphones that can access essentially all human knowledge instantly. We have productivity software that compensates for our limited working memory. We have statistical tools that overcome our poor intuitive understanding of probability. We have collaborative platforms that allow coordination across thousands of people, far beyond the 150-person limit of evolved social cognition. The question isn't whether to use these tools. We're already using them. The question is how to use them wisely. How to leverage technology to enhance our cognition without allowing it to atrophy our native capabilities. Because here's the tricky part. Every cognitive technology comes with trade-offs. GPS navigation gets you to your destination efficiently, but atrophies your spatial memory and navigation skills. Spell check catches typos but may reduce your attention to spelling. Calculator apps perform complex math instantly, but can weaken your number sense. The key is recognizing that technology should augment our Stone Age brains, not replace them. Use GPS to explore new places, but occasionally navigate without it to maintain spatial skills. Use spell check, but also read extensively to internalize spelling patterns. Use calculators for complex calculations, but do mental math regularly to maintain numerical fluency. The goal isn't to reject modern tools. That's impossible and pointless. The goal is to remain cognitively engaged, to keep your Paleolithic brain active even while using modern enhancements. Sleep is another area where the mismatch is causing serious problems. Your ancestors slept in synchrony with natural light cycles. No artificial lighting, no screens, no alarm clocks forcing them awake before their sleep cycles completed. They probably slept more than we do, somewhere between 8 to 10 hours per night, with variations by season. And critically, they slept in darkness. True darkness, not the light-polluted, screen-illuminated semi-darkness of modern bedrooms. Sleep is when your brain consolidates memories, clears metabolic waste products, and performs essential maintenance. Chronic sleep deprivation, which describes most modern adults, impairs cognitive function across the board. Attention, memory, decision-making, emotional regulation, all degraded by insufficient sleep. Studies show that sleeping 6 hours a night for 2 weeks impairs performance as much as staying awake for 48 hours straight. But people adapt to chronic sleep deprivation without realizing how impaired they are. They think they're functioning normally. They're not. Optimizing sleep might be the single most effective cognitive enhancement available to most people. Darken your bedroom completely. Avoid screens for an hour before bed. Keep consistent sleep and wake times. Allow enough time for 8 to 9 hours of sleep. These aren't optional lifestyle choices. They're basic maintenance for your Paleolithic brain trying to function in the modern world. Now, let's talk about the future. Because understanding that our intelligence peaked 30,000 years ago raises obvious questions. Can we do anything about it? Should we? Is the future of human cognition genetic engineering and neural implants? Or is it about creating environments that allow our existing capacities to flourish? Genetic engineering is theoretically possible. We know genes that influence intelligence. We could, in principle, select for them, either through traditional genetic screening of embryos or through more direct genetic modification. But the genetics of intelligence are staggeringly complex. Thousands of genes, each with tiny effects, interacting with each other and with environmental factors in ways we barely understand. The idea of designing superintelligent humans isn't impossible, but it's far more complicated than early genetic enthusiasts imagined. Neural implants and brain-computer interfaces offer another path. Direct connections between brains and computers could provide instant access to information, enhanced memory, maybe even new sensory modalities. These technologies are developing rapidly, but they also raise profound questions. What happens to human identity when your brain is directly connected to external systems? How do we handle security and privacy when thoughts can be hacked? Who gets access to these enhancements? And what happens to equality when some people have augmented brains and others don't? There's a third option, though. Maybe the future of human cognition isn't about changing ourselves. Maybe it's about creating environments where our existing capacities can flourish. Imagine cities designed around human-scale social groups instead of anonymous crowds. Work structured around cognitive rhythms instead of arbitrary 9-to-5 schedules. Education focused on developing deep understanding and novel problem-solving instead of memorizing facts that computers can retrieve instantly. Social media platforms designed to enhance real relationships instead of hijacking our social instincts for engagement metrics. We have Stone Age brains. That's not going to change anytime soon. But we can build an information age world that works with those brains instead of against them. We can consciously design our environments, our technologies, our social structures to align with our evolved psychology. That's not going backward. That's using our intelligence, the intelligence that peaked 30,000 years ago, but is still the most remarkable cognitive system in the known universe, to create conditions where it can function optimally. Because here's the final thing to understand. The fact that human intelligence stopped increasing 30,000 years ago isn't a failure. It's not a limitation we need to overcome. The intelligence we evolved then was enough to survive the last ice age, spread across the entire planet, develop agriculture, build civilizations, create art and music and literature, develop science and technology, and eventually leave our planet entirely. We split the atom, mapped the human genome, and sent robots to Mars using brains that haven't changed significantly in 30,000 years. Maybe the question isn't why we stopped getting smarter. Maybe the question is why we ever needed to be this smart in the first place. What were we preparing for? What challenges required this level of cognitive capacity? We used it to dominate Earth. But that seems almost like an accident. A side effect of adaptations that evolved for some other purpose we still don't fully understand. Our intelligence is already absurd, already wildly beyond what most species need. The challenge now isn't becoming smarter. It's learning to use the intelligence we have wisely in a world we built that our brains weren't designed for. That's the real test facing modern humans. Not whether we can enhance our hardware, but whether we can update our software, our cultures, our values, our environments, to work with the ancient, powerful, and still deeply mysterious cognitive system we inherited from our ancestors. We're living with ancient hardware. And honestly, the hardware is fine. It's the operating conditions that need work. So here we are, 30,000 years after our brain stopped growing, trying to figure out what it all means. Let's recap what we know. Peak human intelligence measured by brain volume, cranial capacity, and the complexity of hunter-gatherer toolkits happened somewhere between 100,000 and 30,000 years ago. Then agriculture happened, civilization happened, and paradoxically our brains started shrinking. Not a lot, not catastrophically, but measurably, about 10% smaller than our Ice Age ancestors. The reasons are complex and interconnected. The agricultural revolution traded raw cognitive horsepower for social stability, self-domestication selected for cooperation over aggression, docility over independence, and that came with biological trade-offs. Nutrition changed, diseases spread, and the selective pressures that had been refining human intelligence for millions of years simply stopped applying. But here's the thing. Here's what really matters. We're doing fine. Actually, we're doing better than fine. We're thriving in ways those big-brained hunter-gatherers could never have imagined. We've built cities with millions of people living in cooperation. We've developed technologies that let us communicate instantaneously across the planet. We've split the atom, mapped the genome, and sent machines to other planets. And we did all of this with brains that are technically smaller and possibly less powerful than the ones our ancestors carried 30,000 years ago. How? Because individual intelligence was never the whole story. What happened after the peak wasn't a decline into stupidity. It was a shift from individual cognitive capacity to collective knowledge systems. We stopped needing to remember everything because we invented writing. We stopped needing to figure everything out alone because we built educational systems that could transmit accumulated knowledge across generations. Your Ice Age ancestor with his bigger brain had to know how to track animals, predict weather patterns, identify hundreds of plant species, craft tools, navigate by stars, and remember the entire oral history of his people, all in his head. No books, no internet, no schools. You don't need to do any of that. You carry a device in your pocket that contains more information than any human could learn in 1,000 lifetimes. You live in societies with specialists, experts, institutions designed to preserve and transmit knowledge. Your individual brain can be smaller because you're plugged into a collective intelligence network that spans the entire species. This isn't weakness, it's evolution, just a different kind. Cultural evolution instead of biological evolution, and it's been far more powerful, far more rapid than anything natural selection could have achieved. Understanding this, understanding our cognitive heritage and our current limitations, matters for how we move forward. We need to stop romanticizing the past, stop imagining our ancestors as supermen with abilities we've lost. They were remarkable survivors, absolutely. They developed the basic mental toolkit that still powers everything we do today. But they were also terrified, often hungry, frequently sick, living brutal, short lives in a world that was constantly trying to kill them. We've traded some individual cognitive capacity for longer lives, better health, more comfort, and the ability to build on accumulated knowledge rather than starting from scratch every generation. That seems like a pretty good deal. The real question facing modern humans isn't whether we're smart enough. Clearly we are. We've built a global civilization. We're tackling climate change. We're developing artificial intelligence. We're beginning to edit our own genomes. The question is whether we're wise enough. Whether we can use the intelligence we have, individual and collective, to solve the challenges we've created. Whether we can cooperate on the scale necessary to address global problems. Whether we can think beyond our immediate survival and plan for futures hundreds or thousands of years away. That's a harder question. And ironically, it might be a question our big-brained ancestors were better equipped to answer. They lived in small groups where cooperation was essential and obvious, where the consequences of bad decisions were immediate and clear, where planning for future generations wasn't an abstract moral challenge, but a practical necessity. We live in a world where the consequences of our actions are delayed, diffused, hard to perceive until it's too late, where cooperation requires coordinating millions or billions of people across vast distances, where planning for the future means making sacrifices today for people we'll never meet. But we have something our ancestors didn't. We have their gift, the intelligence forged in 117,000 years of near extinction, refined through hundreds of thousands of years of selection passed down through countless generations of survivors, and we have 30,000 years of accumulated cultural knowledge built on top of that foundation. The intelligence we have is enough. It's gotten us this far. It can carry us forward, if we're wise enough to use it. If you enjoyed this deep dive into human cognitive evolution, hit that like button. Drop a comment telling me where you're listening from. I always love seeing how far these videos reach. And subscribe if you want more explorations of human history, evolution, and the deep past that shaped everything about who we are today. Thanks for watching. Or listening, if you fell asleep somewhere around the bottleneck. Sweet dreams.